food and cooks it. So let's talk about fire and bipedalism. Fire was important to the commitment to bipedalism. So it's important to talk about this commitment to bipedalism because our ancestors were living in the trees primarily. Coming out of the trees meant that we needed to have some kind of protection. So spending more time out of the trees and on the ground required the use of fire, meant that we needed to be able to have a fire at night instead of living up in the trees to keep ourselves safe from predators. And what we know now is that no species can be both bipedal and live in the trees. So remember I said that those 2.5 million year old Australopithecines had short legs and long arms still. One of the features of bipedalism is having long legs and short arms. So really Homo erectus was completely bipedal, but was still pretty good at climbing trees. And we think that they were good at climbing trees because they were actually very heavily muscled. The move to true bipedalism meant this need for protection at night because they could not very effectively escape into the trees. In addition, if you think about the foods that we find on the ground versus the foods that we find up in the trees, the foods on the ground a lot of times are much tougher and harder. So foods that grow in trees, especially high up in canopies, are usually a lot of fruits, mostly fruits really, some soft leaves. Chimpanzees do a little bit of hunting where they'll hunt other monkey species. I should say other species of primates who are monkeys. Chimpanzees are not monkeys. And then if we think about foods that grow on the ground, yes, we have fruits and berries, but we also have a lot of nuts, a lot of roots, a lot of tough fibrous materials that do need to be cooked before they can be eaten. So also eating more meats meant that they need to be cooked. A lot of people ask about eating meat raw, and we can digest a certain amount of meat that is raw. You know, fish is a little bit different. It doesn't have the same proteins that mammal meat does. So when we eat something like beef raw, your body can digest certain amounts of it, but not that much. We don't create enough of the enzymes to break it down. So if meat turned into being a large portion of these Homo erectus diets, these ancestors' diets, then it needed to be cooked. I also wanted to cite here a study that Wrangham talks about in his book on page 61, and you won't be reading an excerpt from his book. This section will suffice just fine. But this egg study that he did, a lot of raw foodists argue that eggs are the perfect food to eat raw, that they're this wonderful whole protein that's great to eat raw. Arnold Schwarzenegger made eating raw eggs really popular in the 80s when he was a big bodybuilder. And the nutritionists wanted to know, if we're doing it all wrong, if the vast majority of society eating cooked eggs was kind of wasting their time. So what these nutritionists did was they fed chickens, egg-laying chickens, these stable isotopes that are that would be passed through the digestive tract. So they gave the chickens these isotopes in their feed, and the chickens ate them, and when they produced the eggs, those isotopes were then encapsulated in these eggs. The chickens laid the eggs. They gave the eggs that had these stable isotopes raw to some raw food eaters, and then they also cooked some of them and had people eat them cooked. Now, the ones that were cooked, the isotopes had not been degraded, so there were the same number of isotopes in the eggs, and the people who ate the raw eggs actually, because they collected what came out the other end, passed far more of these isotopes through their bodies than did the people who cooked their eggs. So what this told nutritionists is that by cooking the eggs, your body actually absorbs more of what the eggs have to offer than if we do eat them raw. So this was just kind of an example of a study, and I'll go a little bit more into raw food eating a little bit later. But our ancestors, in order to get the most they possibly could out of their foods, cooking was probably very, very important to them. So, controlling fire, I've got some information for you here, and there are some big dates and big names. Now, some of you are anthropology majors, so I wanted to include all of the an in-depth account, not all, of the archaeological information we have regarding fire. If you are not an anthropology major, I just kind of want you to get some of these times. Like I want you to know Homo erectus dates. I want you to know a couple of these dates. So, the big question, when did hominids gain control of fire? Evidence is really inconsistent before the last 250,000 years, but these are the ones that we do have. So you don't need to know the names of these sites, but I have bolded here, 400,000 years ago in England, we have the remains of ash and we have flint. Now, flint is important, and if we were in the class, I would ask you why flint is important, but I want you to think about flints because this means that they had a toolkit to make fire. So in association with the sites that have fire, we're finding these flints saying, okay, they weren't just coming across wildfires and taking a burning ember from them. They actually had control over them, which indicates that these go back much further. In Germany, we have burned flint, burned stick in the shape of a fire poker, a lot of hearths, the remains of ashes. And then next to the Jordan River, we actually have a date that goes back 790,000 years. That's close to 1,000,000 years. We see burnt seeds, wood, and flint showing up over and over and over again. Sites older than 1.5 million years ago have yielded burned bones. And this is significant because burning the bones means that they possibly could have also been cooking the meat before they threw the bones in the fire. So it is unlikely that they were eating raw meat off of bones and then tossing the bones in the fire. They may have cooked them, eaten the bones, and then cast them off, and they still were burnt. We also see heated clay and heated rocks arranged in hearth-like patterns. A hearth is a site where a fire is burned continually over and over again. So that's as far back as about 1.5 million years ago that we believe that fires were being kept habitually, and this date really lines up well with a lot of the changes we see in Homo erectus. Okay, so why did our ancestors start to cook food? A lot of animals actually show a preference for cooked foods. Really, preferring cooked foods implies the ability to recognize high energy foods. So, sweetness, softness, and tenderness indicate high caloric foods. Now, I want you to stop for just a second here and think about hard foods and soft foods. Now, with the exception of like butter brittle or lollipops, these processed foods, if you think about natural foods, softness and tenderness and also sweetness indicate higher calories. Toughness, hardness, lack of sweetness, those typically are more vegetable sources and are not as high in calories. Now, we also have to remember here that our ancestors were in search of calories. They were not trying to avoid calories quite in the way that we are. So the effects of cooking include providing extra energy. And we'll talk a little bit more about this process in a few minutes, but by softening the foods, we're basically pre-digesting them. So when we do put these foods into our mouths, like with those eggs, when they start making their way through our digestive tract, they already are broken down a little bit so that they can actually, the energy can go to our small intestine and we can start extracting the energy from them. If our body is still trying to kind of break apart the molecules to get to the energy, we might miss out on some of that energy absorption or nutrient absorption. Some more benefits might have been these fireside meals, and again, if we think about gathering a community of people, a group of people around a fire, and sharing food and sharing stories, and, if your family provides food for my family, we create this kind of debt within our community where I want to pay back the debt that is owed, and I want to provide food for your family next time. And then we start to kind of create these relationships. Cooking also made a lot of foods safer. And allowed us to consume a lot more diverse food options. We also see a more predictable food supply during periods of scarcity. So if we can take very tough fibrous foods and cook them or boil them down even, we can create a more diverse food supply for ourselves. And this helps when there is less food or if there's a drought. Okay, so here's the question. Is cooked food better than raw? I mentioned the egg study, but that's really isolated to one type of food. So I wanted to cite this Giessen raw food study. And this study was conducted on 513 raw foodists who ate at least 70 to 100% of their diet raw. And by raw, they can do a few things within these raw diets, not just eating raw foods. They can, they sprout some foods. They allow like seeds and some vegetable sources to sprout. They also use low heat ovens, and I believe their limit is 200 degrees. So they don't cook anything over that 200 degree limit. And what we saw is that women lost an average of 26.5 pounds, and men lost an average about 21.8 pounds. Overall, the body fat in over 50% of the women was reduced below levels for healthy reproduction. So this is really interesting in that if the women's body fat falls below a certain percentage, and I think that number is about 16%. I may be incorrect on that. But if it falls below a certain percentage rate, women stop having menstrual cycles. So 10% of these women suffered from irregular cycles, leaving them unlikely to produce. 50% of the women fell so low that they stopped having menstrual cycles, period. That's it. And then an additional 10%, so 60% of these women were unlikely, if not unable, to reproduce. Basically, the findings of this study show that raw foodists are extremely thin, and they're really subject to a lot of health risks. These include increased exposure to deadly toxins from the foods they're eating, pathogens in the foods they're eating, decreased bone mass in the back, hip, and then, of course, coming back to that, infertility. So we're talking about very, very serious side effects. Now, based on what we've learned about hunter-gatherers so far, what is the likelihood that the early hominids had a strictly raw diet? They were active people. They were moving consistently. They had to reproduce at a certain rate in order for this species to become very, very, prolific. So it really is unlikely that they were eating raw. It's far more likely that they were eating their foods after cooking them. Okay, so the energy theory of cooking says basically that cooking helps our bodies better extract energy from food. And this is by externalizing part of the digestive process. So we're going to talk about the following three things here: gelatinizing starches, denaturing proteins, and softening everything. Okay, gelatinization, and this is just a simple line drawing over here on the right-hand side, and you'll need to know these two for the quiz. So gelatinizing, you can see the top half of this image shows this arrow. This is basically heat being introduced, and starches are kind of just these pockets of energy, and they are encapsulated. Once we add heat, they kind of shrivel and soften up, and by doing that, our bodies do not have to go in and attack these pockets in order to extract the energy. If we have to do this, if our bodies can't get through this barrier, we pass the vast majority of this potential energy through our bodies and it comes out the other end whole. Now, if we heat them first, we're softening these barriers, our bodies can come in and yank out all of these really wonderful sources of energy to use them very quickly. So, gelatinization occurs whenever starch is heated. Heating up starch weakens the bonds, causing the tight crystalline structures to loosen, leaving the chains unprotected. So once we do that, now our bodies can go in and attack them really quickly. The more starch cooks, the more it gelatinizes. So the more it does this, the more easily our enzymes can get in and completely digest these starches. Starches are a really fantastic source of very fast energy, and energy in the form of carbohydrates. And carbohydrates are our body's first place that they go for energy. Your body goes to carbohydrates first, basically fat second, and then other body tissues third. So when we do look at, the cooked starch, it yields a lot more energy than raw starches because we are going in and we are pre-digesting and causing these to become very weak so that our bodies can get a lot more from them. Denaturation is the process that happens when we heat up proteins, and you can see here these uncooked proteins. These are actually, we can't make them on a PowerPoint, but these are 3D structures. So they're tightly wound 3D structures, and when we heat them, what we're actually doing is we are causing them to loosen and unravel. So when we heat up proteins, the internal bonds weaken, and this allows greater exposure of them by our digestive enzymes. So our digestive enzymes can hack and get away at some of this, but a lot of it isn't going to be pulled apart. And this not only stops us from getting the energy from these proteins, but it's a lot more work for our bodies and can cause some digestive problems. So we heat them up, they kind of lay flat, they unravel, and our bodies can get at and attack these proteins a lot more efficiently. Heat is not the only source that promotes denaturation. Acidity promotes denaturation and actually causes denaturation. If you've ever had pickles, a lot of marinades do some of that denaturing of meats. Lemon juice, if you've ever had ceviche, lemon juice actually basically goes in and cooks the seafood, so shrimp and other fish sources, and gets them denatured so that our bodies can more quickly and effectively digest them. Drying, things like beef jerky, and then salt. We used to salt fish. We'd have huge barrels of salted fish to last us through the winter, and it goes in and salt pulls moisture out of cells, and when it pulls the moisture out of these cells, it causes a drying that allows for different, you can do fish, you can do pork, you can do beef, you can do lots of different proteins, but when we're pulling out the fluids, we're pulling out the hydration, we're making it so that they are more stable and don't go rancid or rot. Okay, so I want to go back to this image, and we looked up here and we saw those heads that were really important, and then we talked a lot about these middle areas. And now what I really want to do is focus our complete energy on the gut area. And, I didn't give you a disclaimer at the beginning of this, but we are going to be talking about our guts a lot in this class, and we're going to be talking particularly in the next lecture about the colon, because the colon plays a really important part in eating low-quality foods. So over here with the Australopithecine, remember we have this really big, wide gut area, area where the gut can be housed. And over here with Homo erectus, we're talking about a much smaller area, and this is very similar to anatomically modern humans. So all of this gets back to something called expensive tissue theory. And this is the big theory that I want you to take from this unit and into the coming units. Basically, expensive tissue theory says that brains and guts are both greedy for glucose. Glucose is energy. The ability to develop a big brain required a reliable source of these high quality foods that contain glucose for energy. The modern human brain requires 20% of our basal metabolic rate, but only makes up 2.5% of our total body weight. So, modern humans, we have the largest brain to body size ratio of any living animal on the planet. Our brain to body size ratio is greater than anything else living today. So we've got these big old brains. It takes 20%, a full 20% of everything that you consume and process to keep your brain going, because your brain is very, very, very hungry for glucose and energy. We got to keep the brain moving. That's only 2.5% of your total body weight. So this proportion tells us that powering the brain is in fact really, really important. So among species that have the same relative basal metabolic rate, meaning your metabolism, extra energy going to the brain has to be offset by a reduced amount of energy going elsewhere. So if they were to have similar size brains, they would have to reduce the energy going somewhere else. This is where this whole brains and guts things comes in. So the gut size of animals is actually linked to the quality of their diet. And this basically just says that with a large gut, we see animals eating really low quality diets, lots of fibrous foods like grasses and leaves and, bamboos and barks and things like that. When we see smaller guts, we see high quality foods being consumed, meaning that a lot of times they are cooked. So the relative to body weight, primates with smaller guts prove to have larger brains. So over and over and over again, primates with small guts had large brains, indicating that there is actually a point at which the bodies of our ancestors were kind of making decisions. Where do we put energy? In the brain or in the gut? We do not see animals with very, very large guts having very, very large brains. So if we look back at primates, chimpanzees have guts that are large, compared to ours, but small for primates. And they are omnivores, so they make use of a lot of different food resources. Their brains are still small, but they're actually bigger than gorillas when we look at the brain to body size ratio. Gorillas have enormous guts and relatively small brains. They also happen to be what we call folivores. They eat leaves, foliage, all day long. So we're going to be looking over and over again at the relationship between the brain size and the size of the gut. So what does this mean for human evolution? Changes in diet influence the course of human evolution. What caused that divergence of Australopithecine from primitive chimpanzees? What was the big deal, that caused the change from foliage to higher quality foods? There was a change to these habiline, these early hominids, about 2.5 million years ago. It probably was a shift toward eating roots, consuming meats, processing methods of raw meat that allowed them to start growing their brain. The changes to Homo erectus 1.8 million years ago was probably due to the regular consumption of cooked food. We're talking about a rapid increase in brain size and also the reduction of the gut size. So if we remember back to the boxes that we just looked at with just the guts isolated, from here to here, we're talking about an incredible decrease in gut size and quite a big increase in brain size. So how did human brains continue to increase in size after this time? It likely can be explained by advances in cooking processes and the discovery of new foods that are available through cooking. So we kept adding and adding and adding to our, collection of foods that can be eaten. And this gave us a great advantage because we could continue eating in times of famine and in times when food was pretty scarce. So it's probably just this continued diversification of food sources, and then also surviving through those times of famine. There definitely have been famines and extinctions happening in these last 1.8 million years, and it is likely that humans are alive today because we were able to adapt and diversify over time. Okay, so that's it for today for our section on catching fire and the ideas of how cooking made us human. Next unit, we're going to be looking a little bit more into the guts of humans. So we are going to be talking about, we're going to get real personal, talk about your intestines and your colon even, and, what the different functions are of the different areas of the gut. So prepare yourselves for that, and just kind of get further into the types of foods that we eat and how we are solving the problems of getting all the nutrients that we need. So have a wonderful week, everybody. Take care, and bye-bye.